effect analysis of cross-project bugs on software ecosystems. So I'll pass it along to Ma, who will be our presenter today. So yeah, let's go to Mar. And Mar, can you please unmute and start?
Hello, everyone. My name is Ma Wang Ying from Nanjing University. I'm very happy to report our research about impact analysis on cross-project bugs. Nowadays, projects are depending on each other, forming complex software ecosystems. Through the interdependencies, bugs in an upstream project may affect other downstream projects. These bugs are called cross-project bugs. They bring new challenges on software maintenance. Let's look at the following example. SEPA is an upstream project in scientific Python ecosystem. A bug was found in the SEPA API. The API produces wrong results when the input array is of one dimension. Fixing the bugging method requires changing the output values and has met break some downstream projects. So SEPA's developers were very cautious to repair their bug. They asked the downstream developers for suggestions. After Scikit image the downstream project, developers inspect their code, they found that there are no use of the SEPA API in the bug-inducing precondition. However, this still provides some suggestions to SEPA's developer. After a long debate, the SEPA's bug was fixed. However, after 6 months, hello?
Hello, can you share your screen again?
Oh, yes.
Sorry about that. Okay.
Sorry.
Yeah, go ahead. You have plenty of time.
Oh, okay. After 6 months, another downstream project, Nilan, they report that they are very unhappy about the fix because the fix broke the code and without any warning. They spent much effort in debugging the problem, tracing back to the fix. From the discussion, SEPA's developer were completely unaware of the fact that Nilan was using the functionality until that time. So from the real world example, we know it's difficult to provide an appropriate fix if the upstream and downstream sides were unclear about the possibly affected downstream code from before starting to design a fix. For the upstream side, the developers may have no idea which downstream projects are using the buggy function, making it very difficult to collect bug fix suggestions from the downstream developers. For the downstream side, they are not
Hello, Ma, can you hear? Yes, go ahead.
it's not hard to see that analyzing cross-project bug impact requires a lot of painful manual effort. So to solve the problem, we present an ecosystem-wide bug impact analysis to identify the affected downstream modules with a given upstream bug. Note that an upstream function containing the bug is invoked in a downstream module doesn't mean
Hello, Ma. Can you still hear us? Hello, hello. Maybe she's having some internet issues.
So, Professor, maybe we can play the video.
Okay, so maybe in that case, yeah, let's play the video for Ma.
Okay, okay.
So what I'll do is, yeah.
Yeah, we will be playing the video.
Okay.
Okay, thank you, Professor.
We have some background sound. Can we remove it? So yeah, unfortunately, Ma had some video errors. So we'll just play the video for you. And then later on, we'll cross live to her and then see if we can ask some questions. So please ask questions in the Slido, in the chat. I'll be checking those too as well. We cannot hear sound, sorry.
Systems in which projects depend on the infrastructure or functional components provided by other projects. For example, SciPy is an upstream library in the scientific Python ecosystem and has a significant number of downstream projects dependent on it. Here, we call bugs found in a project which affect many other projects in the ecosystem through interdependencies, cross-project bugs. In our previous investigation, we found that more than 17% of bugs are cross-project bug ones on average. Most of these bugs have wider impact on other projects. For example, this NumPy bug affects more than 20 downstream projects. Another example comes from SciPy, a famous Python scientific computing project. Bug found and reported. Fixing the bug requires changing the output interface and hence might break some downstream projects. A SciPy developer thought that if they fix the bug in the upstream project, some downstreams, for example, scikit image, will break. Then he asked downstream scikit image people for feedback. However, after a lengthy inspection of their code, scikit images developers reported that there is no use of the bug method that satisfies the failure triggering conditions, and hence the bug may not concern their project. Still, scikit image developers provide several suggestions, and the bug was eventually fixed after lengthy debate. Then the bug was fixed. Unfortunately, 6 months later, a developer of Neuron reported, and they complained the fix since it broke their code without any warning. They spent much effort in debugging the problem tracing back to the problematic fix. The real-world example discloses that it is difficult to provide an appropriate fix if the upstream and downstream sides are unclear about the possibly affected downstream code before starting to design a fix. So we say that to provide a satisfactory fix, the upstream side have to identify the affected downstream projects in order to communicate the proper person for frustration. The downstream side needs to identify which parts of things are affected in order to provide suggestions and work around the bug on an early stage. So our objective is an ecosystem-wide bug impact analysis to identify the effective downstream models of a given upstream bug. And we face two challenges. The one is that which downstream models are using the upstream bucket method to deal with this problem, which concern lack of ecosystem-wide interdependent inter-project codependencies and scalability and version sensitivity. The other problem is that which downstream uses satisfy the bug-inducing preconditions, and we should concern the efficiency and the complete coverage. This is an overview of our method. For each model, all statements and defect trigger conditions from the entrance of the model to the call point are encoded into symbolic constraints, and the constraints are solved to determine whether the model is affected. Our framework contains two parts: ecosystem-wide dependency analysis and the intra-model impact analysis. The first part is an ecosystem-wide dependence analysis. The goal of the ecosystem dependence analysis is to construct a version-sensitive dependence network over the target ecosystem, which is accomplished by the dependence analysis and the version handler. Within the target ecosystem, each project is processed independently to better handle the dynamic evolution of the ecosystem and to achieve scalability. First, for each project with a base version of the project as the input, the dependence analyzer leverages fine-grained function invocation relations to construct a base dependence network. Then the version handler processes successive versions of the project incrementally by comparing function call changes to add version-specific information to the network. Note that while the network is stored as a central database, its construction and update are modular and distributed to individual projects. Hence, when a project is updated, only the dependencies related to the project may be updated. Such a design substantially reduces the maintenance overhead. Given an upstream bucket function, the model selector can easily identify the candidate downstream models using the dependence network. The second part is an intra-model impact analysis. The intra-model impact analysis takes three resources as inputs. That's individual candidate models, a bucket upstream function, and the failure-inducing preconditions extracted from bug reports. It analyzes each candidate and identifies whether the candidate is truly effective. We say a model is truly effective if with some legitimate inputs to the model, the bug in the upstream function can be triggered. Specifically, the intra-model analysis consists of three subcomponents: the code preprocessor, the constraint encoder, and the SMT solver. The code preprocessor reduces code with rich syntax to a simple form. We analyze three failure-inducing preconditions: type, value, and property. The constraint encoder symbolically encodes paths to the call size of the upstream function, as well as the failure-inducing conditions. The constraints are then passed to the SMT solver. If it is satisfiable, the analysis model is considered effective. Our evaluation aims to answer two questions. The first is how effective of our method, and the second is how efficient. Our database includes 31 cross-project bugs with NumPy and SciPy as the upstream projects, involving 22 projects with 121 versions. Here is the result. First, there are more than 25,000 candidate downstream models, and after analysis, there are only 1,132 affected models. That means that we prune more than 95% of the candidates, and the average precision is about 92%. And here is the efficiency. The most time-consuming part is the dependency analysis. It takes about 50 hours, and the intra-model impact analysis takes only less than 1 second on average. And the conclusion, our objective is for given cross-project bugs, identifying the affected downstream models. We have two contributions. One is an ecosystem-wide cross-project bug impact analysis method. The other is a version-sensitive cross-project dependency network construction method. Thank you.
Yeah, thank you very much. So I think with Ma and the team, unfortunately, we were having internet issues, so we will move on to the next presentation. But I think, yeah, if there's any questions or stuff, we can also contact. So yeah, let's go to the second presentation. So Agus, please share your screen and unmute yourself. And Agus will be presenting to us sieve, helping developers sift wheat from chaff via cross-platform analysis. Great, Agus, please, the floor is yours.
Thank you, Paula. Hi, everyone. Thanks for joining the session. My name is Agus Sulistia. I'm from Telkom Institute of Technology, Surabaya, Indonesia. On behalf of other authors of this paper, I'd like to present our empirical software engineering journal paper. Our work is basically an approach that helps software developers to exploit knowledge from software development specific platform to automate tasks in other less software development specific platforms. So let's take a look at this use case. The first use case we want to explore is when a software developer acts as a knowledge seeker on Twitter. Large number of software developers, they use Twitter frequently to support their professional activities. However, they face challenges while using Twitter due to huge amount of irrelevant tweets produced on Twitter. Therefore, there is a need for a solution to help them to filter irrelevant tweets. And then for the second use case, consider a software developer who acts as a content creator on YouTube, and they publish a coding tutorial on YouTube. Viewers can leave a comments that express their experience with the videos. However, only small percentage of comments in the videos are content related. Therefore, it's important to filter out irrelevant comments to help the content creators to improve their videos. To address these challenges, we propose sieve, an approach to help automated tasks in a non-software development specific platform. Our approach consists of two stages. In the first stage, we conduct representation learning from software development specific platforms such as Stack Overflow or Software Engineering Stack Exchange. And then we build word embedding models from this data. And then in the next stage, we leverage the model to resolve tasks in the target platform, which is considered as a non-software development specific platform. So take a look at the first use case that we want to solve. The task is on finding software relevant tweets. In the first stage, we extract data from Stack Overflow and Stack Exchange and represent them into word embedding models. We use software engineering Stack Exchange dataset since it has many software engineering related terms. The dataset itself consists around 150K posts, while the Stack Overflow data consists around 21 million posts in total, and we sample around 8 million of them. And then in the next stage, there are 3 steps here. So in general, we formulate the task on finding relevant tweets as a ranking problem, in which we rank the tweets in the order of their similarity scores with the sample taken from the source platform. For the Twitter dataset that we use around 6 million of tweets provided by previous work by Sharma et al. So there are 3 steps in this stage. For the first step, we select sentence taken from the source platform, and then for each sentence, we convert each word into a word vector value using the word embedding models. And then we average the vectors of words belonging to the same sentence. And then at the end, there are n vectors representing the n sentences from the source platform. And then in the next step, we tokenize each tweet into words. And then for each word, we look up its weight from the word embedding models. And then we take the average value of the word embedding for all words within the tweets. And then at the end, we have vectors representing all tweets in the dataset. And in the last step, we calculate similarity between the tweets and each of the sentence taken from the source platform. In this case, we use cosine similarity score. And then the final score would be the average of the similarity score. And then we rank the tweets based on this similarity score. To measure the performance of our approach, we use accuracy at K metric, which is defined as the proportion of tweets in the top K position that are software related. For the baseline, we first compared with the previous approach by Sharma et al. Since we use the same dataset with them. And then we also compare with word embedding models, which is trained on Twitter. And then we also compare with a model that use TF-IDF vectors generated from Stack Overflow data. And then as a result, based on our experiment, the result shows that our model, which is trained on software and engineering stack exchange, perform best in terms of all accuracy at key measures. The results also shows that our model improves all accuracy at key scores up to 28% as compared to previous approach. In our paper, we also explore the second use case about finding information YouTube comments, and we also provide discussion about the impact of varying parameter settings. We also experiment with word embedding learned from the other software-related domains such as Hacker News. So you can visit our paper in MZ to find out more information. To sum up, we propose an approach to exploit knowledge from software development specific platform to automate knowledge seeking tasks in other less software development specific platform. We also experiment with two source platforms, Stack Overflow and Stack Exchange, and to solve problem in less software specific development platform, which is Twitter and YouTube. For the future work, we plan to expand our work to other platform and knowledge source such as Wikipedia articles, software development blogs, README files on GitHub, and software documentation. Thank you very much, and please email us if you have any further question or suggestion. And you can also visit our paper in MZ Journal. Thank you.
Thank you, August, for your presentation. I think we have space for one question. I've seen one question there. So do you assume that the text is different from non-software to software sources? And what do you think the differences is between them, like the text that is there?
So the question is the difference between the sources platform? Is that
non-software and source, like the text. What kind of differences?
Yes, the differences is because for the source, it's more like for the software related terms. We can see a lot of software terms there, while for the target, it's more general. Like in Twitter, you can post anything, or in YouTube, you can post on anything. Yeah. So
there's some similar, some not. Okay, we have another one. Have you tried document embedding, like doc to vec?
Thank you. We have we haven't tried that, and we can try that for the next work.
Okay, good. Thank you very much. Well, I think those are the questions, and yeah, we have to move on because of the time. So thank you very much, August, for your presentation. Really good. So let's move on to the next talk with the next speaker. So please, Francis. So Francis will be now discussing, this is a SEIP paper about sharing at scale and open source software-based license compliance ecosystem. So Francis, if you can hear me, please go ahead, and your screen is great.
Yes.
And please share your video.
Okay, terrific. I think I did. Okay.
Okay, go ahead.
So welcome to this session, as Raula said, on sharing at scale in the ecosystems track. So Arun and I are from Siemens Healthineers, and we are part of a open source software-based license compliance ecosystem that we would like to describe some aspects to in this talk in the SEIP track at ICSI today. So the agenda for this presentation is a very brief introduction to the importance of open source software license clearing, some of the challenges in this area, especially towards the full automation of this topic, what activities are going on in this license compliance ecosystem. This is why we say sharing at scale, and also point out some potential for future standardization and research topics. So starting on the first point, it's very essential to understand that we use a lot of third-party software in our products, not only in our company, but basically in all companies, throughout the world. There's a large and growing amount of third-party software. And I say third-party software mean including open source software and also commercial software components. And the focus here is on the subset open source software components that are in the various products that all of our various companies and other organizations have. And when you buy a software component, it's very important to understand that you do not buy the component as such, as if you would, for example, buy a hardware component, and then you can do anything you want with that hardware component. But when you buy a software component, you do not buy the component as such. You buy the license to use that component in various different ways. And that is why it is so essentially important that you adhere to these license obligations that are associated with the third-party components, open source and commercial, that you're using in your various products. And of course, because of the growing amount of open source software that is in our products, it's important to try to automate this topic. And overall, the reason for this large growth in open source software is that if you choose the communities that you work with carefully and the components that you work with carefully, you can actually have large scale reuse, a lot less effort, often very high quality. It's not a guarantee. So maybe on the challenges side, it's not a guarantee that you have good quality. You have to choose the communities and the components carefully. But on the plus side, you can avoid vendor lock-in. It's a lot easier to upgrade. You can focus on the essential and differentiating activities in your product, and maybe have more of the standardization or commodity parts, for example, in open source. And the whole open source community is so keen on transparency and collaboration, and that's just the way the software engineering community as a whole is going. And so that's why, especially in the software engineering community at ICSE, we can learn so much from the open source community. But we have to make sure that we do our license compliance correctly, and the contributors don't make our life easy. There are not always standard ways of including the license information in the product, in the source code, and makes it harder to automate. There are some other aspects that make the full automation hard to deal with. And also we're dealing with continuous diversity and constant change. But those are things we have to get better at dealing with anyway. So it's really good to focus on this topic. So some of the more concrete problems or challenges, I would say, with license compliance automation is especially important because of the huge amount of open source that we want to try to automate as much as possible. But the number one goal, the very unequivocal number one goal, is that we have to be correct. We have to know what is the license obligations in the software that we're using, and make sure that we adhere to them. So that's number one. And then take that off the table, and then within that we have to try to do this as much in an automated way as possible. And whether you're using commercial-based approaches to do open source license compliance, or whether you're using open source-based approaches for license compliance, in either case, there are still a number of challenges related to the full automation. Some of the licenses, for example, have dual licenses or multiple licenses, and you have to be able to handle these cases appropriately. It's sometimes a challenge to really accurately identify which version of the license do you have. There's also some discussion regarding, is the main license good enough, or do we go all the way down to the file-based license, the file level license? In our case, we do this on the file level. Here you have to imagine you have components inside of components inside of components, n levels deep, and you have to actually go all the way down that chain to make sure that you are aware of and can handle correctly the licenses, even on that most detailed at the leaves of this tree. And sometimes there's incomplete, redundant copyright information, and this has to be clarified. So this is something where we need to also involve humans in the loop, license compliance experts, to make sure that we handle this correctly. And there is basically software engineering research topics in this space that could help us push the envelope a little bit further to increased automation. And in this part of the talk, Arun and I would like to point out some of the work that the Linux Foundation has done in this space. So there's an automated compliance tooling project that the Linux Foundation has about license compliance tools. And there's a number of projects that are involved here. I think many of you have heard of SPDX, the Software Package Data Exchange. It's a de facto open standard for describing what we call the software bill of material. What is the set of software components that are in a particular product? And we need to know this not only for the licenses, but also for handling the cybersecurity appropriately, to know which components do we need to track for security vulnerability, for example. And other projects in this automated compliance tooling projects are Fossology, which is an open source scanner recognizing licenses in a very good way. There's also the open source review toolkit, which has a specialty of being able to very much identify all of the dependencies of this project. Often you have a whole set of transitive dependencies in modern software systems that you need to recognize and be able to handle. And also Quartermaster is another important tool in this space. And finally, the project Turn, which is especially good in the area of handling containers. And the other major Linux Foundation project in this space is about how the key requirements for open source compliance program are set. So this is the Open Chain project of the Linux Foundation. I refer here at the bottom to the URL. So the Open Chain project is also includes a set of companies that have shown that they are conformant to these requirements for a quality open source compliance project. And they have a set of tools. There's a reference working group that I will show on the next slide that is working in this space. So this is a slide showing sort of the overall process for this topic. On the left side, you have coming in your own proprietary software, as well as the commercial third-party components. And in the case of this talk, most importantly, these third-party software open source components that are coming into the process. And then it goes through all of these steps of scanning for the licenses, looking for the license text in the source code, resolving issues, producing the appropriate records so that we can produce, for example, the README files that go out with many of the products describing which licenses are used, to produce all the documents we need on the right hand side, the appropriate notices and attributions for copyright and so on. So this is the overall recommended approach. And this is a slide based on OpenChain's curriculum. So there is it's a very good resource for further information on this topic. There is a very large set of documents describing open source license compliance and how to do this correctly. This is showing some of the tools that are in this open source tooling work group of OpenChain. You see at the bottom a pointer to the GitHub site if you're looking for further information on how to help any of these tools to become even better, or work on research aspects associated with any of these. These show the set of tools that are in this case, a continuous integration, continuous delivery kind of infrastructure. So you can see some of the tools that I had already mentioned at the bottom left, Fossology and also ScanCode as different scanner things that can do license scanning. And then later on, for example, the OSS Review Toolkit and Software 360 Antenna. And there's many different companies supporting and other communities supporting each of these tools. And this group of, open source enthusiasts are together in this open source tooling work group and are working on how can we work together on improving the ecosystem of open source based license compliance tools. How can we make sure that the interfaces between the various tools are open and transparent? Over on the left, you can also see software heritage. This is a very interesting topic where they're trying it at Software Heritage, not only trying, but actually doing, to have basically all of the source code from many, many different products, and that has been developed in the years of software engineering on the planet. And being able to tap into this to be able to further improve how well we can handle the license compliance in this space. And then moving on to the final part of the presentation, in the area of the automations, there are some things, for example, in the area of machine learning that we have some initial steps in the community on all of these topics, but would be interested not only from our company, but also in general. I think all of the members of this open source reference tooling group would also be interested in contact on how to improve some of these topics with research ideas. But for example, in the machine learning for license identification, we typically use a rule-based approach for identifying licenses because this is a way that is particularly accurate. It's most important to be 100% accurate at recognizing the license. But there are also some ways that machine learning can be of use in this space. But that gets into some issues, for example, you'd call it, I think, biased training set. There are thousands of different open source licenses. And if you were to apply machine learning on that whole set, that would be maybe not so appropriate because there's a huge bias. There's a set of like 100 different licenses that are very, very commonly used, like MIT or Apache and so on. But then there's some other very unknown or hardly used licenses. Anybody could invent their own license. And so you don't have any training data or very little training data for some of those very seldomly used licenses. So you would have to maybe consider doing machine learning on the set where you have really enough information on. On the normalized structure of the license texts, this is a challenge we have in the automation. It's not really so much a research challenge, but a challenge in the area of standardization. How can we encourage the community, maybe through upstream contributions, to have a more standard way of describing the license texts in the components so that it makes it easier for the automation.
Francis, we probably just have a bit of time left, so
yes.
We're pushing a bit for time. So maybe we can just fit in some questions.
This is actually the last slide. Yes, yeah. And so thank you for your attention. We also have decider agents.
Yeah. So can you show your face if you can, and then maybe we'll just have one question that you can answer, and maybe there's a question here is. What is the practice with open source components at Siemens? Like, do you adopt it for your own use, or do you try to keep it untouched?
Sorry, could you repeat the question?
Sorry, what is the practice with open source components? Do you adopt it for your own reuse, or do you just keep it untouched? Like, do you reuse it? Do you clone them open?
Well, we at Siemens and at Siemens Health Engineers, and also all of the companies involved in this community, they have used these tools to recognize the components, and then we explicitly try to reuse the components, also to reuse the component clearing report. So if there is a particular component that is used, we do the license on that component, and then we reuse that through when a different product or uses that same component. So we have a strategic a group that defines strategies and policies for the topic of open source compliance so they handle it appropriately.
Okay, all right, yeah. So yeah, thank you for that. I think what you meant is you reuse it. So yeah, we had some difficulties, but yeah, thank you for that. If you have more questions, I think you can just ask and you can answer them to see them in Silla. So we'll go on to the next speaker.
Yes, that would be fine.
And thank you so much for your time and really interesting talk about licenses in the ecosystem. So our next speaker will be Ivica, who is going to do an extended abstract of software deployment to heterogeneous platforms, a systematic mapping study. So
yes.
Ivica, can you share your screen?
Yes,
and
I
you can play your video.
You can see me. Hello. So my name is Ivica Crnković, and I will present a paper about moving to heterogeneous platform. And since the main author was my PhD student and he prepared an excellent video, so I will run this video, and then after that, I'll answer to the questions. So here I start with the video.
Hi, my name is Hugo. I'm here to present our work about software deployment on heterogeneous platforms. This work has been conducted at Chalmers University of Technology in Sweden by myself, Jan Schroeder, and Ivica Crnković. Let's jump right into it. In the context of this work, heterogeneous platforms refer to hardware platforms containing more than one type of processor, such as CPU and GPU or CPU and FPGA. There has been a shift in industry to use this technology, which allows for higher levels of performance in computer systems, basically faster execution time and or lower energy consumption. However, these architectures are inherently different, requiring changes in the process of engineering software in order to have it running and utilizing all capabilities of the hardware. In addition to the difference in numbers of cores, other aspects like memory management must be explicitly handled by the programmer. Furthermore, software deployment is a key aspect due to the need for allocation and mapping of software components onto the different processors that are available. So the main research question of this work is, what is the state of the art of software deployment on heterogeneous platforms? We wanted to obtain an overview of the area by focusing on two main perspectives, concerns and approaches. Through RQ1, we discovered the aspects of interest when software is deployed on heterogeneous platforms, as well as the issues that typically arise in the process. Through RQ2, we discovered the general and recurring approaches for deploying software on heterogeneous platforms. In order to answer the research questions, we conducted a systematic mapping study, which typically aims at obtaining a broader picture of the research area when compared to classic systematic literature reviews. This method includes multi-step screening process on studies retrieved from different sources, based on a set of predefined inclusion and exclusion criteria. In our case, the screening resulted in a set of 146 primary studies that were summarized and categorized to answer the research questions. The results also include other aspects in addition to the research questions, such as the main purpose of the studies, type of research, and type of validation that was used. In the figure, we see that the majority of the hardware platforms reported in the studies contained a combination of CPU and GPU. Several concerns were found, mainly related to scheduling of tasks, software quality, and software architecture. In scheduling, there were several discussions on load balancing, issues in scheduling tasks, kernels, and whole applications, including the problem of proper resource utilization. In software quality, some quality attributes were discussed as challenges when deploying software on heterogeneous platforms, including performance, portability, and efficiency. In software architecture, the discussions were around the issue of efficiently managing data and memory, given that the memory spaces are often separated and the data format across the different processing units is not homogeneous. There were also discussions on the development process, focusing on difficulties in achieving efficiency in the process and the complexity of parallel programming. Hardware was also widely discussed, even though we focused on software engineering aspects. The authors highlighted the attempts of reducing energy consumption, as well as issues related to design and maintenance. Some studies discussed the importance of evaluating the overall system through performance analysis and methods to visualize the behavior of heterogeneous systems. Finally, there were a few studies discussing the challenges of simulating such systems in order to predict their behavior. The approaches we found were separated into design time practices, runtime practices, and general practices, which are orthogonal to binding time. Under general practices, we found several approaches discussing development frameworks like OpenCL, CUDA, and OpenNP. Several studies proposed novel load balancing techniques based on aspects such as performance of the processor, aspect-oriented techniques, and bandwidth constraints. Also, some known algorithms in computer science were reportedly used in the context of scheduling, such as the greedy algorithm and earliest deadline first. When it comes to design time practices, we found some techniques to model software and hardware, such as performance models and hierarchical task graphs. The latter is also used to define software-hardware configurations, exploiting the characteristics of each target hardware architecture. Finally, when it comes to the runtime practices, we found several studies describing the implementation of their own scheduler, with different priorities depending on the context. Profiling and task queuing using either global or local queues were also reportedly used in some studies. As shown previously, most concerns in the field are related to the scheduling of tasks, processes, kernels, and most proposals are independent of the deployment binding time. The vast majority of studies propose solutions to problems rather than evaluating or validating them, which indicates a certain immaturity of the field of research, despite the fact that the concept has been around for a few decades. There's a clear lack of tool validation in practice, as well as holistic approaches to software engineering that cover refactoring for execution on heterogeneous platforms, which we are particularly focusing on at the moment. That's it for today. If there are any inquiries, don't hesitate to contact us via email. Thank you for watching.
Okay,
so now I'm looking at the Q&A. Silla, we don't we don't have so much, but maybe I'll just ask one quick one because we are up for plan. So recently we've also seen AI and software engineering and machine learning and those aspects. So I think based on your study, do you have some comments on these studies? Are they increasing, and how does it affect the architecture, like with the platforms?
Yes, thanks for the great question. So while we have seen in the literature, it's a lot focus on a particular aspect like performance, energy use, and so in practice, there are many companies which are struggling today how to move, in particular starting to use AI, because both the processes is changed and then the infrastructure, both in the development time, but then at the runtime. You know, like when you have cyber physical systems like cars, suddenly if you are performing machine learning algorithm, you need the powerful processors in the machine. And that requires quite a lot of work. And it is really a challenge at the companies which maybe it's not yet recognized in the research community as an important problem. So that certainly that AI and machine learning increases a lot new challenges with moving at runtime to heterogeneous platforms.
Okay, thank you so much for your very interesting talk. And yeah, that was for the next talk. So yeah, we'll move on to our final talk, which is going to be given us by Lingfeng Bao. And it's a large-scale study of long-time contributor prediction for GitHub projects. So yeah, please go ahead.
Wait, sorry, wait a moment. Can you see my screen?
Yes.
Okay, so I will start. Wait a moment. Hi, my name is Lingfeng Bao from Zhejiang University, and I will present our work, a large-scale study of long-time contributor prediction for GitHub projects. This paper has been accepted by GSE, and the co-authors are Xinxia from Monash University, David Lowe from Singapore Management University, and Guillaume Murphy from University of British Columbia. And the background of our study is that the open source project has many contributors. However, only a small of them can stay with the project for a long time. So if we can identify potential long-time contributors earlier, there are several benefits. For example, project maintainer can take some action to return more contributors, and the project maintainer can also understand what facts are more important. And there are few studies that but this study based on a small number of projects and a limited set of information. For example, bug reports. And in our study, we use a large-scale dataset that is more than 900 projects on GitHub, which contain different developer activities. And in our study, we defined a long-time contributor to be a contributor who stays with a project for more than a certain time. That is the time interval between the first commit and the last commit of a contributor to the project. In our study, we use 3 different settings, that is 1 and 3, 1 and 2 and 3 years. And we use a data dump of judge torrent, which contain different kind of developer activity. For example, commits, issues, pull request. And we filter the projects by the following step. First, we select top 1,000 projects sorted by the number of their start. Then we filter the project whose program language is empty. And we also filter the project that doesn't use GitHub as the issue track system. And we also filter the fork projects and the delete projects. Finally, we get 970 projects. And this table shows the number of long-time contributors and non-long-time contributors. And in our study, we built prediction models based on the first month of developer activities of newcomers. And we extract a total of 63 features in 5 dimensions, that is developer profile, repository profile, developer monthly activity, repository monthly activities, and the collaboration network. And in our study, we want to answer 4 research questions. The first one is, can we effectively predict what a developer will become a long-term contributor of our project soon after they submit their commit to the project? And the second one is that how the effectiveness of the prediction models built on all features compared with those built on only a subset of features. And the third one is we want to identify the important features. And the last research question, we want to investigate the effectiveness of the cross-prediction prediction. And for the first research question, we use time series cross-validation. We divide our dataset into 10 no-overlapping windows, and we also use different parameter settings for prediction models. And we use AUC to evaluate the prediction models in our study, and we found that random forests have the best performance. And for the second research question, we found that the prediction models built on all features have a better performance than those built on a subset of features. And for the third research question, we identify the important features by the following steps. The first is the correlation analysis, then we do the redundance analysis, and then we identify the important features and compute the effect of important features. And we found that 8 features belong to the top 10 most important features in all 3 time interval settings. For example, we found that the month user commit in the dimension of developer monthly activity has a negative impact, which indicates that the workload of a project might have a negative impact on developer being a long-term contributor. And for the last research question, we wanted to investigate the effectiveness of the cross-project prediction. And we have 3 different settings, that is cross-project language, and cross-project size. And we found that our prediction models have a very good performance. This table shows the result of the cross-project predictions. And finally, we also wanted to get some feedbacks from developers based on our studies. So we design a survey. In this survey, we let the response to rate their agreement on the 3 most important features found in our study, and we also want them to comment any other facts. And finally, we received about 115 responses. And for the results, we found that many responses agreeing or strong agreeing that this important feature have big impact on developer being a long-term contributor. And they also provide 3 other categories of facts, such as project quality, project community, and personal facts. And here are some example comments from the survey results. And that's all. Thank you.
Okay, thank you very much. So maybe we actually have a press for time, but maybe very quickly. Did you feel like your survey results also complement or they contradict what you found in your prediction models?
Pardon?
Sorry, did the result from the feedback, did they also correlate, or was it the same as you found in your models, or did you find that it's different?
Several facts is different. For example, some personal facts we cannot model in based on the data used in our study, because this personal facts it is very difficult to model this personal facts, I think. So the feedback in the survey, they provide here are some comments. Here, for example, this comment says that the personal factor is that how important that a project is to the contributor. So this such factor it is very difficult to model, I think.
Okay. All right. Thank you very much. So yeah, we've come to the end of our session with the 5 great talks. We had some difficulties with internet, but I think we got through most of them. So I think if everybody can give a hand, and yeah, if you have any questions, you can contact the authors yourself. So this is the end of the session, and thank you very much.
session of ICSI 2020. This session is about API and commits. And we'll have 6 exciting presentations today, 1 journal first, 3 research papers, and 2 near papers. So we'll start with the first presentation, which is a journal first paper, Accept on IEEE transaction software engineering, and is going to be presented by Xinjiang Zhang. Please.
Okay, can you see my screen now?
Yes.
Okay, thanks for the introduction, Matt. I'm Jinxuan Zhang from Nanjing University of Aeronautics and Astronautics in China. In this talk, I will introduce a new method to enrich API documentation with code samples and corresponding usage scenarios. And this work has been accepted by TSE. As we know, reusing APIs in existing libraries and frameworks could help developers speed up their software development. When they facing an unfamiliar API, developers tend to consult API documentation for help. However, when referring to API documentation, developers are willing to learn the correct API usages in the context of code samples rather than only read verbose descriptions. Hence, it could be ideal if API documentation can be automatically enriched by code samples and a corresponding usage scenario. And in this work, we propose a new method. Its name is DAC. DAC leverages crowd knowledge in Stack Overflow to identify code samples and corresponding usage scenarios for enriching API documentation. It includes 6 components. The first component is API type extractor. The API type extractor will identify and extract API types from API documentation. Then the second component is question and answer pair search engine. Question and answer pair search engine will generate a series of question and answer pairs from Stack Overflow and link them to related API types. And we use the traceability linking method in this picture to link the corresponding question and answer pair to their corresponding related API types. The next component is question and answer pair preprocessor. It extracts usage scenarios and code samples from the linked question and answer pairs. Especially, we extract usage scenarios from the title of the question and answer pair, and we extract the code sample from the best answer of the question and answer pair, and we combine them together to form a series of usage scenario and code sample tables. The next component is table clustering. It clusters usage scenario and code sample tables for each API type to avoid duplicated tables, as we know that there are a lot of duplicated question and answer pairs in Stack Overflow. Next is the table representation. It selects the most representative usage scenario and code sample tables, achieving the highest user scale in each resulting cluster. And finally, information embedding will embed the top-ranked representative usage scenario and code samples into the corresponding API documentation. And we define a template to organize these tables and embed them into the corresponding API documentation web page. And we investigate 4 research questions in this work. The first question is we investigate the quantity of the API types illustrated with the code samples and usage scenarios in a DAC enriched API documentation. The second research question, we investigate the quality of the code samples in the DAC enriched API documentation with 3 quality indicators, including correctness, conciseness, and usability. Third, we evaluate the coincidence levels between the code samples and usage scenarios in the DAC enriched API documentation. And finally, we investigate whether the DAC enriched API documentation can help developers program. And we invite 21 developers, and we divide them into 3 groups. They are required to accomplish some programming tasks with the help of different types of API documentation. And we can compare the 2 metrics, for example, the task completion frequency and the average completion time. And we can compare different types of API documentation. And this slide shows the result of the first question. We compare 3 types of API documentation: the raw API documentation, and the Xdocs enriched API documentation, and the DAC enriched API documentation. Here, the Xdoc is a baseline approach we want to compare. We can see that the number of code sample illustrated API types is greatly improved in the DAC enriched API documentation. This is the answer to the second question. We compare the code samples in the
1 minute.
1 minute.
Yeah.
Okay. Okay.
Yeah.
And a DAC enriched API documentation, we can see that the quality of the code sample is higher than the baseline. This is the coincidence levels between code samples and usage scenarios. We can see that the code samples are relatively consistent with the corresponding usage scenario. And finally, we compare different programming tasks, different developer groups, and different types of API documentation. Especially when I start with the DAC enriched API documentation, developers can complete more programming tasks within less time. We can start using the DAC enriched API documentation can boost the productivity of developers. Okay, thanks. Thanks. Next.
Okay, thank you very much. And I don't see questions from the audience so far. I do have a question in the meantime. Did you compare with the... okay, I see another question. So let me ask a question from the audience.
Okay.
How vital is the usage of question and answer search engine? Aren't test and code samples an alternative to learn API usage? So basically the person is asking, in case you have non-public software for which you do not have discussion on Stack Overflow, how would this approach work? Or commercial API, for example.
Yes, our work is based on the question and answer pair in Stackflow, and the other approach is based on some general code search engine. But we can say that by leveraging the question and answer pair in the Stackflow, we can obtain the high quality code samples, and the code samples are consistent with the corresponding usage scenario. So we can see that using the cloud knowledge in Stackflow is a better way, I think, to obtain the high quality code samples for enriching API documentation.
Okay, thank you very much. So
okay.
We have to move to the second presentation. Second paper is a new idea paper, and it's going to be presented by Sebastian Nielbock. Please, Sebastian.
Thanks, Max. Hello, everybody. Yeah, assume. So can you see my slides?
Yes.
Okay, fine. So hello, everybody. Assume you are a developer and you wrote this piece of code where you applied the Java output stream API over here, and your goal was to write a long number into this data output stream right there. This data output stream has an inner byte array output stream, and after we wrote that number to the outer output stream, we access this inner byte array output stream with the toByte array method. However, sometimes this outer stream does not directly write the input into the inner stream. Therefore, it is a good habit to flush or close the outer stream so that the input is properly written into the inner stream. if we miss to call this method, this is a kind of an API misuse, and our goal is to detect and correct these API misuses automatically. These are my colleagues Robert Heumüller and Jacob Krüger, as well as my supervisor Frank Ortmeier, and of course me, Sebastian Nielbock. And I'm going to present our work on a cooperative API misuse detector that uses correction rules. Existing API misuse detectors usually consider the client code that may contain an API misuse, and then search in other code repositories or select code in a different way to find similar API usages from which we can infer API usage pattern specifications, or generally said rules that describe how this API has to be used in a correct manner, for example, by using mining approaches. Then we can check our client code against these specifications, verify it, and check whether this code satisfies the specifications or not. And if not, we can detect an API misuse. However, the problem with these automatically inferred specifications is many of them are false positives, causing many false alarms, and therefore harms this approaches to be applicable in practice. Therefore, we consider a different route where we do not consider automatically inferred specifications, but rather real fixes from real developers. So whenever a developer finds and fixes an API misuse in a commit, he might want to share his fix with other developers in a cooperative way. And we automated that so that we can extract a so-called correction rule, where we depict the misuse code as a graph representation A, and the respective fix also as a graph B. So this rule describes how we can transform A, the misuse, to the fix B. Then we use the left-hand side of that rule to search in other code repositories for similar code that may also contain the misuse.
1 minute.
Okay. And then we can check within these code samples whether these code samples contain the misuse part A, but not the correct part B. And then we can notify the respective developers that they may have an API misuse. We evaluated our approach on 43 real-world API misuses and were able to find only 20 valid correction rules. And we also saw that the misuse detection has still an improvable precision recall. Therefore, we have identified some problems. For example, we have to revise our rule generation with an improved type resolution because this causes many invalid rules. We also need different misuse criteria, for example, to cope alternatives, and we need a bigger data set for API misuse, for example, from the Android framework. This also finished my talks. All our data sets and scripts are available on Bitbucket, and now I'm happy to take your questions.
Okay, so there is one question for Foggia. Which technique have you used to search similar code snippets?
So right now we did not implement the searching, but what we plan is we actually have this graph of an API misuse, and we can do some kind of a subgraph isomorphism. So whether this misuse part is also part of this code. Whether this will scale depends. I think we have to do some steps in between. For example, first searching for code that also uses that API so that we have something that actually will scale in practice.
Okay, another quick question. How do you identify API usage fixing commits? Because commits can also contain many other changes. They can be template commits, for instance.
So actually the idea is that the developer itself noticed this is an API misuse and marked this commit by himself. So this is really a human validated API misuse.
Okay, thank you very much. So at this point we go to the third speaker. Third speaker is Hao Xia. Hao, please. And this is a technical paper.
Hello.
Hello.
Can you see my slides?
Yes.
Okay. Then I will start. Hello, everyone. My name is Xia Hao, and I'm a student from Fudan University. Today, I will present our work, how Android developers handle evaluation-induced API compatibility issues, a large-scale study. This is a joint work from with researchers from Purdue University. It is well known that Android is evaluating very rapidly. During Android's evaluation, new APIs are introduced and some old APIs are removed. We can see the figure on the right. In some versions, about 3,000 new APIs are introduced and or 1,000 old APIs are removed. And when app calls these unsupported APIs, it will crash with no such method error. The figure below is a runtime log for this issue. After investigation, we found compatibility checks is the standard way to handle these issues. And we divide these checks into two types, single check and replacement check. Look at the figure A. A single check just checks the compatibility issue with the underlying API level. Here is the check SDK int greater than or equal to 22. Single check is easy to adopt, but may cause inconsistent bugs or experience, as the app do nothing when SDK int is less than 22. The figure B is the replacement check. It provides similar functionality on unsupported API levels. So we think replacement check is a better way to deal with compatibility issues. However, there are several challenges in differing single checks from replacement checks. First is that the control structure does not reliably distinguish replacement check from single check. Some people may think that the single check is just has the if structure, and if the code has if and else structure, it may be replacement check. Actually, this is not true. We can see the figure A. It has if and else structure, but it is a single check because it just print a log on the unsupported API level. And the figure B is the real replacement check. The second challenge is that the similarity between the true and the false branches does not actually differ these two checks. In the below code, two branches are very similar, but the false branch lacks the important function make customer annotation. Despite many challenges, we designed an excellent tool to detect and classify compatibility checks. Rapid has two main components. One is static analyze component, the other is feature extraction component. In static analysis, the tool first identifies compatibility checks by intent analysis. Then it extracts related code blocks for the check. These code blocks will be sent into features extraction component. In feature extraction, Rapid will compare unsupported API with every API in the other branch. By doing data flow analysis, Rapid can extract both behavior semantics features and output dependencies features. These features will be converted into feature vectors or for classification. I will briefly introduce the two feature sets we select. The first feature set is called the behavior semantics feature set. This set has 8 features. They are based on the class name, method name, modifier, and comments of the two compared APIs. Class and package name similarity are splitting a name into a set and calculating the similarity. Common package prefix length and package hierarchical distance are the similarity between packages. API name is like a natural sentence. It contains nouns and verbs. Operation action and the target similarity are the similarity of verbs and nouns. The last is the comment similarity. We transfer the comments into word set and calculate the similarity. The second feature set is input-output dependencies feature set. This set has 11 features. They are mainly about the similarity of arguments and the return value. See the figure below. Input verbal set and output verbal set are based on data flow analysis. Input is the set of blue verbals. Output is the green verbals. Operation set is similar to verb set. It contains the system API invoke in data flow path. Before starting the large-scale research, we first evaluate the effectiveness of our tool. First, we manually analyzed 293 checks to build our training set, which cover 123 different APIs. And then we randomly choose 440 checks for validation. These checks have no overlap with the training set. As we can see, our tool achieved a quite good performance on both data sets. Besides, we also evaluated the contribution of two different feature sets. We find it is necessary to including both feature sets. After proving the effectiveness of our tool, we conducted a large-scale application analysis. Our research have the three main research questions. We included apps from Google Play and third-party markets, including their top-ranked apps. As shown in the table, we include more than 300,000 unique apps. We ran rapid in parallel to analyze these apps and set the timeout for each app to 5 minutes. In all, rapid successfully analyzed about 300,000 apps.
1 minute.
Okay. Only 100,000 apps timeout and 1,000 apps failed to pass by flow dry. In research question 1, we have 3 main findings. Finding 1 is that most apps are affected by this issue. This research shows that compatibility issues are very popular in apps, in Android apps. Finding 2 is the ratio of replacement check is quite low, which calls for improvement. Finding 3 is control flow structure is not reliable in differing single and replacement check. Our tool is very necessary for replacement check classification. In researching question 2, we find, as shown in the figure, Google gives recommendations for some deprecated APIs in the comments. However, only 130 of 2,850 compatibility-related APIs have Google recommendations, while they greatly help developers better handling compatibility issues. As shown in the table, the replacement check ratio of APIs with recommendations is significantly higher than this with no recommendations. At last, some Google's recommendations are not followed for those incompatible API invocations that are not replaced in the recommended way by Google. We further investigate the underlying cases. Overall, we observe 2 main reasons that case developers to handle compatibility issues in a different way. The reason 1 is the recommended API needs more extra. The reason B is there is a quicker replacement exists. In research question 3, we have 2 main findings. We can improve our replacement ratio by implement our findings. At last, in general, our work find and differ 2 kinds of compatibility checks. We design an automated tool to differ single check from replacement check. At last, we perform a large-scale study on compatibility issues. We found fixing evaluation-induced API compatibility checks is still a challenge. So it is important to provide easy adoptable recommendations. And we think mining fixed solutions from experienced developers can significantly help novice developers. Thank you.
Thank you very much. We have a question from Portia Rani. Have you investigated further the deprecation API recommendation from Google?
Sorry.
If I understood correctly, the question is whether you investigated further the deprecation recommendation from Google.
Oh, okay. We have about 2,850 capability-related APIs in our research. We manually searched the Android developer website to find if they have recommendations. So we have about 5 students to help us do this work. This is manually analyzed to find if there exists any recommendations.
Okay. Another quick question for changes of a function argument. Is this a single check or a replacement check?
Which check is a single check or replacement check? Or
well, this was the question from somebody. Maybe you can discuss this point offline. So it's asking whether how the approach works when there is a change of function arguments, basically. Okay, maybe you can discuss this point offline. So we have to move. Thank you again, and we have to move to the third presentation now. This is also a research paper. Is an empirical study on API parameter rules, and we have a video being played for this presentation, but then one of the authors, Nameng, will answer the question. Let's start the video, please.
Haozong from Jiao Tong University. The title of our paper is an empirical study on API parameter rules. This is a joint work with Nam from Virginia Tech. We know that API libraries are widely used. Here, we present some examples. When calling APIs, we must follow rules to prepare their parameters, or else we will introduce bugs in our code. What are parameter rules? There are two types of parameter rules. The first type of parameter rules are document rules. These rules are defined in API documents. For example, this document comes from Lucene. It defines that the value of field must not be null. It also defines that the value of the other two parameters must be within legal ranges. The second type of parameter rules are code rules. These rules are defined in API code. For example, this piece of code comes from an API method of Lucene. It defines that the value of m must be at least 1, or else it will throw exceptions. The API code also defines that the values of the other two parameters must not be null. As for parameter rules, many questions are still open. Here are our research questions. The first question concerns the types of parameter rules. And the second question concerns the distribution of parameter rules. The questions have the values and some of our results are unexpected. But before we present the results, we have to collect as many as possible parameter rules for analysis. It is infeasible to manually collect so many parameter rules, so we implement Parallel to automate the process. Our tool is designed to automate our study. It does not comprehend rules as other tools do. As a result, it does not define any templates. As shown in this table, if a tool uses templates, its extractor rules are limited to these templates. Without templates, it is feasible to find more parameter rules. Our tool identifies both document rules and code rules. It has 3 steps to identify document rules from API documents. It first parses sentences with standard parser and builds syntax trees from sentences. After that, by traveling the build syntax trees, it selects sentences that have at least one model verb. From these sentences, it removes those if their model verbs appear in subclauses, because we found that such sentences typically have no rules. Our tool has 2 steps to find code rules. First, it builds syntax-dependent graphs from API code with Silla. After that, it extracts slow exceptions and assertions that are related to parameter rules. We notice that the graph of such exceptions and assertions follows specific patterns. Our tool uses patterns to locate the desirable exceptions and assertions. To evaluate the effectiveness of our tool, we selected 9 projects, and from each project, we select 20 files. We asked 2 PhD students to manually identify the parameter rules and compare their results with the ones that are identified by our tools. As shown in this table, our tool has correctly identified most parameter rules. After parameter rules are identified, we manually classify and analyze the identified parameter rules. Based on our analysis result, we present our answer to the first question. In this table, the columns show the percentage of different categories of parameter rules, and we present examples for each category. The result shows that in total, 69.1 of parameter rules are simple rules such as no values, range limits, and legal values. We compared document rules with code rules. This table shows the distribution of code rules. We found that the top 3 categories are still null values, range limits, and legal values. However, the other categories have few rules because it is easier to document such rules than to implement checks for them. Here is our answer to the second question. We found that document rules and code rules have little overlaps. In total, 86.2% of parameter rules have only code rules, and 10.3% of parameter rules have only document rules. For those overlaps, we found that 3.5% of parameters have inconsistent document and code rules. Only 1.5% of parameter rules have inconsistent parameter rules. We notice that even if parameter rules are inconsistent, they are not necessarily bugs. For example, the following code slip comes from Paul. Its documents and code define different rules. Whether they are inconsistent, they are both correct, and this is not a bug. In summary, API libraries are quite useful, but we shall follow parameter rules to call them. In this paper, we conducted an impure study to understand parameter rules. To support this study, we implemented a tool. Our tool can correctly identify most parameter rules. In total, it extracted more than 1,000 parameter rules. After our manual inspection, we found that about 70% of parameter rules are simple rules such as null values, legal values, and legal ranges. In addition, we found that code rules and document rules are little overlaps. Only about 1% parameters have inconsistent rules, and such rules are not necessarily bugs. This is the end of my presentation. Thanks for your time. If you have questions, please send us emails. We're happy to answer your questions.
Thank you very much. All right, so now we are going to have to answer questions, and while somebody will start to ask question on Slido, I will try to ask the first question. So now, how do you think your results could possibly impact program repair techniques and tools?
So say it again. What things are related to techniques?
Yes. So basically, my question is, basically, you studied different kind of parameter rules, and I was wondering whether your findings can be useful to improve program repair research, to help program repair research.
Yeah, I think it's possible. So currently, we observe that the existing API automatic mining tools for the parameter, automatic mining tools for the parameter rules are not sufficient because either they are based on this natural language templates, or like they fully rely on the source code to identify this error exceptions throwing. And in the future, I think some potential things we can do is that we can further improve the existing parameter rule mining tools so that we can find more rules automatically, more precisely. And then with those rules, maybe we can also provide some API recommendation tools so that if people invoke the APIs with the incorrect parameter values, incorrect formats, we will automatically provide suggestions to correct them.
Yeah. Another question from the audience, from Pooja Rani. Did you consider the annotation, like a Javadoc annotation, like @param in API documentation in order to select your API rules? So did you consider those annotations?
So currently, we mainly focus on the Javadoc annotations, like each time we.
Yeah, exactly.
Yeah, and so for this Javadoc annotations, our current approach is that we rely on some simple templates. If this statement contains some modal verbs, let's say must, may, maybe must, or maybe should, something like that, and then we just automatically include them into this pool of like potential API parameter rules, and then do the manual checking. And the one threshold validity here is that if the rule doesn't contain this must or should, but it also emphasizes that something should follow some rule, then currently this approach may not reveal those kind of constraints or API parameter rules.
Okay, very, very quick question. Are the heuristics template and the tool available?
I think so.
Okay, thank you. Thank you very much again now. And now let's move to the next presentation. Next presentation is a new idea paper. Is going to be presented by Ming Wen. and is about booting automated program repair with bug-inducing comments.
Can you see my slides? Hi, everyone.
Yes, thank you. Yes, thank you. Go ahead.
Okay. Good afternoon, everyone. My name is Mingwen, and I'm from Huazhong University of Science and Technology, China. It is my great honor to present our new idea track paper, which is boosting automated program repair with bug-inducing commits. And this is a joint work with SOSTECH and the Hong Kong University of Science and Technology. We all know that automated program repair has gained huge attention recently from both industry and academia, and lots of approaches have been proposed, among which search-based APR is a major category. However, one of the long-standing and challenges of the search-based APR is the search space explosion problem, in which case the correct patches are outside of the search space, and or the search space is huge, and the correct patch cannot be found within the time budget. The search space is collectively defined by the fault space, fixed space, and ingredient space. So the fault space is usually refined by the fault localization techniques, and many other heuristics have been proposed to refine the fixed space and ingredient space. For example, researchers have proposed to learn from the big code data, specifically they learn from how bugs from open source projects are frequently being fixed. Therefore, they learn patterns and then design mutation operators to repair new bugs. However, in this study, we are proposing a new direction to refine the fixed space and ingredient space. And this is inspired by observation that developers are often looking for the information of bug-inducing commits when debugging in practice. Therefore, the key idea in our paper is that instead of learning from how other bugs from open source projects are frequently being fixed, when refining the fixed space and ingredient space, can we directly learn from how the bug was introduced? Specifically, can we search for mutation operators and fixed ingredients from the project's version histories, especially from the inducing commits for when designing APR techniques? So here we show a concrete example of our patch OZ, and here we show the fixed commit and the inducing commit. And we also extract the mutation operators and the fixed ingredients, and we can see that they are highly correlated. So the mutation operators involved in the inducing commit are highly correlated with those involved in the fixing commit. To further validate our idea, we performed an empirical study based on the defects4j benchmark. Specifically, we have recovered the information of bug-inducing commits for 91 bugs out of the over 357 bugs. And we then extract the mutation operators and the fixed ingredients for both of the inducing commits and the fixing commit of a same bug. And here we show some preliminary results. First, we compare the mutation operators, and here we show the ratio of mutation operators that could be inferred from the inducing commits across different projects. And we can see that actually the mutation operators to fix the bug can be inferred either directly or inversely from the associated bug-inducing commits for a substantial number of cases. And we then compare the fixed ingredients, and we can see that substantial fixed ingredients can be inferred from the bug-inducing commits, especially for those with a few tokens. And for those can be inferred, there are many involved in the inverse actions when compared to fix the bug compared with the ones that introduce it. So based on these observations, we propose a simple heuristic. First, we try to revert the whole changes together with the associated ingredients involved in the inducing commits. If we cannot repair the bug, we then try to search for a subset of the changes together with the associated ingredients, and then try to revert the whole patch. And here we show some results. And in total, 11 bugs can be fully repaired and 1 bug can be partially repaired using our strategy. Among them, 8 bugs have never been reported to repair by the existing techniques. So such results indicate that the direction that is to leverage the inducing commits in automated program repair is promising. We also have 2 major important next steps, which are to better infer the mutation operators based on the inducing commits, and we also need to design more sophisticated rules to infer the fixed ingredients. And that's all, and more details can be referred to our paper, and thanks very much.
Thanks a lot. Okay, let's see if there are questions from the audience. at the moment. Okay, so in the meantime, a question from my side. You know, there have been approaches that try to learn program repair from huge code bases, like from GitHub bug fixes using deep learning. So
Yes.
I'm wondering what will be the advantage of our approach with respect to just learning from many changes, like from GitHub or something like
Yeah,
that.
that's how existing works do. That they try to learn from a large number of code. However, in our study, we do not plan to learn from a large number of code changes. Instead, we only want to learn from those changes that are related to this bug, mined from the project's its own history instead of from other projects. How to obtain such changes? We might perform some dynamic testing to find some related changes, and then we extract some mutation operators from those related changes instead from those inferred from frequent patterns or something. Yeah.
Okay, thank you very much. Perfect.
Thank you very much.
So we move to the last but not least presentation of this exciting session. So the last presenter is Imad Agayani, and is going to talk about software documentation from a practitioner perspective. Please, Imad.
On the screen.
Okay.
So it's clear, right?
Yes.
Okay.
Please go ahead.
So I can remove this thing. Okay. So hello, good afternoon and good morning, everyone. My name is Imad Agayani from River Research Group at Software Institute in Switzerland. Software documentation issues like outdated or incorrect content have become an inevitable part of developers' life. Last ICSI, we presented a research study focusing on such issues. In summary, we manually inspected a large number of artifacts discussing documentation issues from different data sources. And based on that, we built a detailed taxonomy of documentation issues, followed by an in-depth discussion of these issues, their concrete examples, and we propose actionable suggestions to address them. Although the taxonomy is comprehensive, it is too detailed to be used by other external researchers and practitioners, and it's not validated by practitioners. So this paper aims to address these issues. In particular, in this work, we revisited our taxonomy and compressed it by keeping only key issue types. Then, in collaboration with ABB company, we conducted 2 surveys aiming to answer the following 2 research questions. First, understanding documentation issues which are relevant to practitioners. Answering this research question can guide researchers in the development of tools and techniques aiming to identifying and addressing the issues which are relevant to practitioners. With our second research question, we are interested to understand the type of documentation which are relevant and is useful for practitioners when they perform a specific task. This information is essential in the development of future recommender system whose goal is to generate documentation. Starting with the first item in our agenda, to limit the number of issues in our taxonomy, we first organized our taxonomy into 3 parts. Then we merged together issues which are very similar and share the same parent category. As a result of this process, we ended up with 51 issue types out of originally 162 issues. This is the new set of issues that we got. First group refers to issues with documentation content, like what is written in the documentation. Second group is related to how documentation is written and is organized. And the third one groups issues linked to documentation process and tools. Moving on to our first research question, we conducted a survey with 78 software professionals, mostly employed by ABB company. The survey basically asked developers to select the documentation issues which are relevant to them or they face them frequently. Based on the collected responses, as part of the paper, we report the percentage of participants that consider each of these issues important, how frequently participants face these issues, common solutions adopted or suggested by practitioners, whether these issues affect readers, writers, or both, an in-depth discussion of interesting cases shared by practitioners, and finally, possible future research directions in this scope. As an example of our discussions, let's take a look at the second group of issues related to how documentation is organized. As we can see, documentation clarity is the issue which is perceived most important by practitioners, as it affects them in many ways. Considering documentation users and their needs into consideration, and verifying documentation by someone who has little domain knowledge and highlighting the essential information elements in documentation were among proposed solutions by practitioners. In this scope, future research can be devoted to automatically testing software documentation and also studying documentation elements which are essential in each type of documentation. In fact, our second research question goes toward these latter directions. As I said, our second research question is about to understand which type of documentation, like code comments, API references, and so on, which are useful to practitioners when they perform a specific software-related activity, like code refactoring or programming. For that, we conducted a second survey with 68 software professionals. Given a random documentation type, like API reference, participants were asked to answer 3 basic questions. In which task does this given type of documentation come in handy? What is the rationale behind your choice? And which elements in this documentation is particularly useful? We answered this research question by analyzing a heat map depicting the percentage of participants who considered each documentation type being useful in each different tasks. The darkest spot in the chart indicates that a high percentage of participants consider that documentation being useful for that task. The first and most noticeable message here is that practitioners do not perceive all documentation types as useful for different tasks. In addition to reporting the percentage of participants who considered each documentation type being useful in different tasks, we also discussed the reasons provided by practitioners why they chose a specific task for a specific documentation, as well as the information elements which are particularly useful in that documentation. Let's take a look at one example. Looking at the chart, participants considered code comments being mostly useful for 2 quite related tasks, namely software debugging and program comprehension. This again confirms that the context is important when we propose information to developers. When we ask participants about their choice, they stressed that code comments communicate information that is not evident in the code, which is essential for those who join the project in the later stages. They also highlighted the fundamental role of parameters description and developers' assumption in software debugging as the most useful elements within code comments. So to wrap up, in this paper, we revisited our last year work and we refined our taxonomy to make it more usable by external practitioners and researchers. Then we investigated the documentation issues which are relevant to developers, and we reported the common solutions suggested by practitioners, as well as the possible future research directions in this scope. And lastly, we investigated the type of documentation and its elements which are considered being useful in different software-related activity, as well as the rationale behind such choices. We believe our findings can be leveraged in the development of future recommender systems aiming at automatically generating software documentation. Thank you for your attention, and I'm happy to answer your questions.
Thank you very much. So, Imad, we have different questions from the audience. The first question is from Alexander Servenik. And the question is about whether some of the dimensions you investigated, like clarity, could be subjective. So, for instance, clarity could be subjective because people with different information processing strategies will find the same documentation either clear or unclear.
Okay, thanks for the question. This is true, but to address this concern, what we did was in the survey we proposed a description and a definition for each of these documentation issues to make sure that the developers or participants understand what we mean with each of these documentation issues. For instance, when we talked about documentation clarity, we gave a number of examples of what we mean with documentation clarity. For example, when the documentation is not clear means the parameters are not described in the correct way, and so on. So by proposing definition, we try to address this issue, this concern.
Okay, thank you. Then there is another question from Pojerani. How did you prepare the survey? And then if the survey questions are available for replicability.
Okay, for designing, I mean, the survey content is already publicly available in our replication package, including all the questions, the choices, and the definitions we provided to participants. Regarding how we built the survey, we used Qualtrics, which is a service that you can make survey with it, which is something provided by my university. So we chose it because it was available to us.
Probably the question was more about how did you assemble, how did you define the question from a more methodological point of view?
Okay. So it was something that we did inside with the authors. So the first author, which was me, I proposed a set of questions, and then we started reviewing this question with other authors in several rounds, and we go back and forth with different questions. At the end, we ended up with this set of questions that we have in the survey.
Okay, and finally, there is a question. There is a question about whether the issue of finding a suitable documentation has been considered. So whether sometimes it's possible or not to seek suitable documentation.
Yes, I'm not sure if I can bring it up, but yes, we have this issue under the category of findability, which is a parent category, and there are other sub issues. One of them is the difficulty to find the suitable documentation. And this is exactly what he is asking for.
Okay. And then a very last question from my side. So within companies, especially for commercial API, for closed source, what's the alternative for informal documentation we know as Stack Overflow? So they have, do they have any alternatives to Stack Overflow for informal documentation, like mailing lists or internal repository, something like that?
I cannot recall if the participants mentioned any specific platform for like similar to Stack Overflow internally in the company. Maybe this is not, they cannot do that to disclose such information, but I cannot recall any such platforms inside from the ABB.
Okay, thanks again, Ima. So this concludes the session. Thanks to all speakers and to the audience for having asked a lot of questions. Of course, there were also a few questions that we could not let the speaker answer, but you can go on the exhibit hall for each in the room for each paper, and you are strongly encouraged to continue the discussion. Thank you very much, and bye-bye.
Thank you, Max. Thank you for the organizers.
Thank you.
Thank you.